When you start talking about physics, at first you will normally learn about two main types of motion: uniform and accelerated motion. So, what is the difference? Uniform motion, when you travel from point A to point B, you will contain the same speed throughout your entire trip. When going from point A to point B at an accelerated motion, you will change speeds. You may speed up, you may slow down, almost to a stop even. But because you're changing speeds, it's considered an accelerated motion. So what we're going to do is simply drive our quad in our driveway, once at a uniform motion and once at an accelerated motion. We're going to time how long it takes for us to reach the end of the driveway each time. As well, we are going to track the speed that we are going. So, after we do this, we can then do some equations to find out the distance traveled at different times. This is for both uniform and accelerated motion. We can also do equations to find the velocities at different times. So, when we get our distances and our velocities later for different times, we can then make some nice position time graphs and velocity time graphs that we can use to compare the difference between the two. We can compare how far they go in the amount of time, and we can compare the change in velocity in uniform and accelerated motion. So, let's just jump into it. Uniform motion. We are calculating distance at 5 different points: 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds. From our video, we can see that our speed throughout is 7.0 kilometers per hour, which is equal to 1.94 meters per second. We can tell that this is 1.94 meters per second from 7.0 kilometers per hour from the simple conversion 7.0 kilometers per hour divided by 3.6 equals 1.94 meters per second. So this is our speed all throughout in these next 5 equations. So the first equation, we have time is equal to 2 seconds, and we are looking for our distance. Speed, 1.94 meters per second. Distance is equal to our speed times our time. So our distance is equal to 1.94 meters per second times 2.0 seconds. We can cross out the S's on both of these numbers because when we multiply them together, they cancel out. This leaves us with only meters for our distance, which is 3.88 meters. Due to significant figures, we have to round this to 3.9 meters. For t equals 4 seconds, distance equals speed times time. Distance is the unknown still. Speed still the same, 1.94 meters per second. So we do the same thing, except we multiply it by 4 instead of 2. 1.94 meters per second times 4.0 seconds. Again, we can cancel out the s's. This leaves us with 7.76 meters, which when we round it is equal to 7.8 meters. Same equation again, except we are using 6 seconds this time. Distance is equal to speed times time. Distance equals 1.94 meters per second times 6.0 seconds. Again, we can cross out our s's, and this will leave us with a distance of 11.64 meters, which we round to 12 meters. When time is equal to 8 seconds, with the same speed, 1.94 meters per second, we do the multiplication of 1.94 meters per second times 8.0 seconds, distance equaling speed times time. That gives us 15.52 meters, which when we round is 16 meters. And finally, at 10 seconds, speed 1.94, looking for distance. Distance still equals our speed times our time. Distance equals 1.94 meters per second times 10.0 seconds. Distance equals 1.94 meters. In all these scenarios, we cross out our s's, leaving us with a distance of just meters. When we round our 19.4, we get 19. So the distances that we find now can be used to make a position time graph for uniform motion. So, when doing accelerated motion to find distances, it's a different ball game from uniform motion. Uniform motion, you can just go distance equals speed times time. However, accelerated motion, you can't do that. D equals VT is a uniform motion thing only in physics. So, before we can find the distances, we need to find the average acceleration. We can do this if we can use our velocities at 0.0 seconds as v1 and 10.0 seconds as v2. Our velocities will be converted from kilometers per hour to meters per second by dividing by 3.6, like we did in uniform motion. I won't be showing it here, but it will be done. So our V1 equals 0.0 kilometers per hour north, which is equal to 0.0 meters per second north. Our V2 is equal to 16 kilometers per hour north, which is equal to 4.44 meters per second north. Our average acceleration is unknown, and our time we are using is 10.0 seconds. So V2 equals V1 plus our average acceleration times time is the equation we need to use to find our average acceleration. Now, we plug in our numbers that we're given. V2, 4.44 meters per second equals V1, 0.0 meters per second, plus our average acceleration times our time, which is 10.0 seconds. Where the V1 is equal to 0.0 meters per second, we can just get that out of here. We can take it out. We can cancel it out. It works out nicely. It doesn't change anything, so we're just going to get rid of it. So 4.44 meters per second is equal to the average acceleration times 10.0 seconds. Next thing we have to do to get the acceleration by itself is to divide by 10.0 seconds on both sides of the equation. This will leave us with our average acceleration equal to 0.444 meters per second squared. And when we round, due to sig figs, we are left with 0.44 meters per second squared for our average acceleration. From here on, we can go and do our distances for our position time graph, where again, we're going to look at the distances for 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds. So, our distance is unknown. Our time, we are using 2 seconds. V1, because we start from a stop, is 0.0 meters per second north, and our average acceleration is 0.44 meters per second squared. And please note at the bottom, for 0 and 2 seconds. For 0 to 2 seconds. That's very important. So our distance is equal to V1 times the time plus the half of acceleration times time squared, which is equal to 0.0 meters per second times 2.0 seconds plus half of 0.44 meters per second times 2.0 seconds squared. We only square the 2.0 seconds, remember. And again, we can get rid of the middle part of the equation, because when you multiply 0.0 meters per second by 2.0 seconds, we're left with 0. So distance is equal to the second half of the equation, 1/2 times 0.44 times 2.0 squared. When we plug that into our calculator, we're given the distance of 0.88 meters. And we don't need to round, because we already have 2 significant digits, and that's what it comes out to. So, therefore, our distance for 0 to 2 seconds is 0.88 meters. The rest of the equations for the accelerated motion distances. Now we're going to talk about 2 to 4 seconds. Every time we use a time of 2 seconds, because we're using 2-second time periods, 2 to 4, or 6 to 8, or 8 to 10, or 0 to 2, 4 to 6. You get the idea. So, at this time, our V1 is equal to 1.111 meters per second north. Our time is 2, and then we use our same average acceleration for all of the equations, which is 0.44 meters per second squared. So our distance is equal to V1t plus half of AT squared. That gives us distance is equal to 1.111 meters per second times 2.0 seconds plus half of 0.44 meters per second times 2.0 seconds squared. And remember, only 2 is being squared. That means D equals 2.222 plus 0.88, which is equal to 3.102 meters, which we round with 2 sig figs to 3.1 meters. For 4 to 6 seconds, we used a V1 of 2.222 meters per second north. So distance equals V1 times time plus half of acceleration times time squared. So we plug it in. Distance equals 2.222 meters per second times 2.0 seconds plus half of 0.44 meters per second squared times 2.0 seconds squared. This will give us a distance equal to 4.444 plus 0.88, which is equal to 5.325 meters. And when we round it, it's equal to 5.3 meters. Next one, 6 to 8 seconds. We use an initial velocity of 3.055 meters per second north. So when we plug it into our equation, distance equals V1 times time plus half of acceleration time squared, we get distance equal to 3.055 meters per second times 2.0 seconds plus half of 0.44 meters per second squared times 2.0 seconds squared. This gives us 6.11 plus 0.88 equal to distance, giving us a distance of 6.99 meters that we round to 7.0 meters for 6 to 8 seconds. This time, for 8 to 10 seconds, the V1 is equal to 3.8888 meters per second north. Our time still 2, acceleration staying the same throughout, 0.44 meters per second squared. Distance equals V1t plus half of acceleration time squared. Distance is equal to 3.8888 meters per second times 2.0 seconds plus half of acceleration, which is 0.44 meters per second squared, times 2.0 seconds squared, giving us a distance equal to 7.7776 plus 0.88, giving us a final distance of 8.6576 meters, which we round to 8.7 meters due to significant figures. The distances that we have now found, the 5 distances, can be used to make our precision time graph for accelerated motion. So, precision time graphs from our equations. So, for uniform motion, we have a position time graph showing our position traveled over a given amount of time. So, we went 1.98 meters per second for 10 seconds in our scenario. This caused us to travel 3.88 meters every 2 seconds. So between 0 and 2, 3.88 meters. Between 2 and 4, 3.88 meters. 4 to 6, 6 to 8, and 8 to 10, same thing. This results in a diagonal line starting at 0 meters traveled at 0 seconds to 19.4 meters traveled at 10 seconds. Now, accelerated motion is different. You can tell already just by looking at the graph. So the big thing about accelerated motion is that you're going different increments of speed every 2 seconds. So that means you're traveling a different distance every 2 seconds. So between 0 and 2 seconds, we went 0.88 meters. Between 2 and 4, we went 3.102 meters. Between 4 and 6, we went 5.324 meters. 6 to 8, we went 6.99 meters. And finally, 8 to 10, we went 8.6576 meters total. That means that we are not going a uniform motion because we have different increments of speed every 2 seconds. Now, normally when you look at an acceleration time graph, a position time graph for accelerated motion, you would see a nice J shape with a nice curve going almost straight up. However, we don't have this in our scenario. This is because we didn't increase by a large enough increment of speed as time was going through. Like normally, it would start the same, 0 to 2, and about that, and 2 to 4. You're pretty good throughout there too, up to 4 seconds. But after 4 seconds, you normally start to see it go to about, from 4 to 6, you'd see it go about to 8.5 meters traveled. Really starts to go up like a J. Now, because we didn't increase by large enough increments of speed, we didn't see it. However, if we did go by a large enough increment of speed, that is what our graph would look like. However, it's not in our case. So, those are our position time graphs. To find uniform motion velocities, to make a velocity time graph, all we need to do is take our speed and add the direction we traveled, which was north. We went 7.0 kilometers per hour, or 1.94 meters per second. So, our velocity equals distance over time. If we had a distance of 3.888 meters, we put that on top, and we take our time, 2.0 seconds, put it on bottom, do the division, it comes out to 1.944 meters per second north, which rounds to 1.9 meters per second north. And we use the same process for 4, 6, 8, and 10 seconds with different distances. For 4 seconds, we use 7.76 meters. Divided by 4 seconds, 1.94 rounds to 1.9 meters per second north. 6 seconds, we use 11.64 meters. gives us a velocity of 1.94 meters per second north. Rounds to 1.9 again. All due to significant figures. That's why we round. 8.0 seconds with a distance of 15.52 meters. We divide 15.52 meters by 8.0 seconds. Velocity equals 1.94 meters per second north, which we round to 1.9 meters per second north. And finally, 10.0 seconds. We traveled 19.4 meters at this time. Our velocity equals distance over time. 19.4 meters divided by 10.0 seconds equals 1.94 meters per second north, which rounds to 1.9 meters per second north. And we can use these velocities to plug in and make a velocity time graph for the uniform motion that we traveled. To find the velocities at 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds, we need to take the speeds we traveled at the given times and divide them by 3.6 to get meters per second, and then add a direction on to our meters per second speed. So our speed at 0 seconds was 0 kilometers per hour. Divided by 3.6, 0.0 meters per second. So when we add on our direction, 0.0 meters per second north, that's equal to our velocity at 0 seconds. 2 seconds, we are going 4.0 kilometers per hour. Divide that by 3.6, we got 1.111 meters per second. So our velocity is equal to 1.111 meters per second north. Our speed at 4.0 seconds is equal to 8.0 kilometers per hour. We divide that by 3.6 to get 2.222 meters per second. Our velocity, 2.222 meters per second north. We were traveling north. So we add north. Speed at 6.0 seconds is equal to 11.0 kilometers per hour. Divide that by 3.6 is equal to 3.055 meters per second. That means our velocity, 3.055 meters per second north. Speed at 8 seconds, 14 kilometers per hour. Divided by 3.6 is equal to 3.8888 meters per second. So our velocity is 3.8888 meters per second north. And finally, our speed at 10 seconds is 16 kilometers per hour. Divided by 3.6 is equal to 4.4444 meters per second. So our speed is equal to 4.4444 meters per second north. The velocity will be used to make our velocity time graph for accelerated motion. Velocity time graphs. First, please remember, velocity is only your speed with a direction added. Now, velocity time graph for uniform motion. The whole time we were traveling 1.94 meters per second. At 2, 4, 6, 8, and 10 seconds, the whole trip. Which means when we are going north, our velocity is equal to 1.94 meters per second north for the whole trip. That gives us a velocity time graph like this. with a straight horizontal line at 1.94 on the y-axis, just below the 2, for 2, 4, 6, 8, and 10 seconds. It's a nice straight line. That's because we kept the same speed, going the same direction, making it the same velocity throughout. So our accelerated motion velocity time graph. So we're increasing speeds for our accelerated motion. So we started at a stop. So our velocity was equal to 0 meters per second north. Now, when we started to move, our velocity started to increase because we were going north. If we were going south or west, we would be going below the x-axis. However, because we're going north, or if we went east, but we went north. But because we're going north, we're going above the x-axis. So, at 2 seconds, our velocity was equal to 1.111 meters per second north. At 4 seconds, our velocity was equal to 2.222 meters per second north. At 6 seconds, our velocity was equal to 3.055 meters per second north. 8 seconds, our velocity was equal to 3.8888 meters per second north. And finally, 10 seconds, our velocity was equal to 4.4444 meters per second north. That gives us the resulting velocity time graph for accelerated motion. And these are both of our velocity time graphs that we got from our experiment.